This work deals with the development of a computational method for the nonlinear analysis of reinforced concrete beams subjected to general constraint condition and monotonic loading. To this aim, a layered beam finite element has been developed with refined kinematic assumption, and so the actual bidimensional displacement field in the beam is here approximated by means of polynomial function, which describes the variation of displacement along the beam height. And further, this model allows to take into account the mechanical nonlinearity of cracked reinforced concrete through the implementation of a SHEAR crack model to evaluate the stiffness metrics in each layer of the beam element. And the procedure is finally validated through comparison with results from literature. The analysis up to failure of beams subjected to bending and shear is a quite complicated task due to the markedly nonlinear response of the material after cracking and due to the interaction between the constituent materials that are concrete and steel reinforcement. And moreover, the analysis is further complicated by the presence of discontinuity regions with high stress concentration and by the possible development of diagonal shear cracks, which may lead to a variation of the strain field across the cross-section I, which is hardly caught by a traditional method. And consequently, these problems are often afforded by means of two bidimensional finite element analysis. The basic idea underneath this work is to develop this layered beam finite element where the displacement field of a generic point of the beam is calculated by superimposing, by summing up two different contributions that are the corresponding displacement at beam center line, which is assumed coincident with the x-axis, and this term which represents this polynomial function which describes the displacement variation along the beam height. And the only unknowns of the problem are represented by the coefficient of this expression that are the generalized displacement, which are only function of variable x. The same relation can be written in matrix form, and this is the generalized displacement vector, which can be in turn expressed as a function of the nodal displacement by introducing proper shape function, which depends on the type of chosen finite element, and in this work an isoparametric 3-node beam element has been adopted. So under the small displacement hypothesis, the strains can be related to the nodal displacement by means of the compatibility equation, and the stress field in each layer of the beam can be evaluated by simply calculating the stiffness metric of the material forming that layer multiplied by the corresponding strain. So the stiffness metric of the material is evaluated by means of the PARC model, which was developed at the University of Parma starting from 2001. And this is a macro model which describes the behavior of reinforced concrete as a continuum material whose properties depends on the properties of the constituent materials and their interaction. And the model has been developed with reference to a membrane element under in-plane stresses, and both the effect of the reinforcement and of cracks are mirrored on the element. The model considers two different constitutive behavior depending on if the element is or not cracked. So in the cracked stage, steel is assumed as linear-elastic, while concrete is treated as an orthotropic material with subjected to a biaxial sale of stress. While in the cracked stage, reinforced concrete is treated as a nonlinear orthotropic material with axis of orthotropy coincident with the direction parallel and perpendicular to crack direction. And the stiffness metric is evaluated by taking into account the contribution due to concrete in compression, steel in tension and compression, and to all the mechanisms that take place at crack surfaces. So the stiffness matrix is calculated by superimposing the contribution due to concrete and steel, and in the cracked stage, all the contributions are expressed as a function of three main variables that are the crack width, the crack sliding, and the strain in the concrete strut between two adjacent cracks. This layered beam finite element has been implemented into a finite element program written in Fortran language. So the program solved the equilibrium system by constructing the stiffness metric, the global stiffness metric of the structure, and the nodal force vector. So the global stiffness metric is evaluated by assembling the contribution due to each element, which is calculated by the classical relation here reported. And this latter is rewritten by taking advantage of the subdivision into layers and by transforming the expression into the intrinsic coordinate system and by using the Gauss integration technique. And it can be observed that parameter Bi represents the average width of the beam in the considered layer. So the model can be applied to general cross-section geometries by simply modeling the boundary of the cross-section by means of straight line segments and assigning to each layer an average width. The nodal force vector is constructed by following the same procedure as before, and it is uploaded at each loading increment since the equilibrium system is solved by means of an iterative incremental procedure due to the nonlinearity of the material. And this is the structure of the program. So there's a first part relative to the insertion of input data, which are relative to control parameters that are, for example, the chosen order of the polynomial expression as well the numbers layer in each element, and also relative to constraint condition. Then also geometrical and mechanical data relative to the examined beam are requested and the external loads. Then the program first evaluates the stiffness metrics of the structure, then constraints are applied by means of the Lagrange multiplier method, and the total nodal force vector is uploaded from the current loading increment. Then the system is solved by means of this iterative incremental procedure. And starting from the displacement, this unbalanced force vector is evaluated and convergent check is performed. So if it is satisfied, another loading increment starts. Otherwise, the procedure is repeated and the stiffness matrix is uploaded based on the current strain field, and the procedure is repeated until the attainment of convergence. The effectiveness of the method has been validated through comparison with the classical results, experimental results, on both statically determined and undetermined beams. As regards static beams, only one beam is reported for sake of brevity, which is a simply supported beam subjected to a distributed load. As regards modeling choice, obviously it has been necessary to model all the beams due to the asymmetric distribution of stirrups. And further, the polynomial function has been used to describe the displacement field. And some of the results are here reported both in terms of global load displacement response and in terms of the evolution of some selected local variable as loading increases, which are very important in order to perform serviceability verification. As an example, here I reported the evolution of the sum of crack width registered at the level of the tensile reinforcement between the midspan and the support, as well as the stressing concrete struts and the stressing stirrups. And the model is able to quite correctly catch the behavior. For example, in case of stirrups, the model catch the fact that stirrups are in compression until the formation of an inclined shear crack which intersect them and then they work in tension. As regards statically indeterminate beams, the results here reported are relative to HH series, which is constituted by 5 specimens with the same cross-section geometry and the same loading and boundary condition, since specimens are a continuous beam on 3 supports subjected to 2 concentrated loads placed in the middle of each span. The specimens differ from the different values of duration between the applied bending moment and the shear force, which is a very critical parameter affecting the shear capacity of the beams. The same model choice is already described and been adopted, but in this case the symmetry has been exploited and consequently only one half of the beam has been modeled. Here are some comparisons between numerical and experimental results in terms of global behavior, so applied load versus displacement under the loading point, while other comparisons are provided only for beam HH4, which was characterized by the lower experimental failure load and by a critical value of the ratio between applied moment and shear force. And here are some comparison in terms of stressing concrete in the bottom chord over the central support, maximum stirrups between the concentrated loads and the central support, and sum of crack width in the central part of the beam and in the lateral wall. And also this graph shows the distribution of normal strain across crack across the cross-section I, and a better agreement between numerical and experimental results can be found in this case by increasing the order of the polynomial function used to model the displacement. And here some comparisons are also provided in terms of concrete stresses at beam extraders and intraders for different values of the applied load. So moving to conclusion, in this work this procedure has been presented, which is able to correctly catch the global and local behavior of beams also in the cracked stage. And satisfactory prediction can be also achieved in discontinuity regions where high concentration of stresses occurs, and so also localized failure can be predicted, and the latter can be usually predicted only by using more complex approaches, like for example bi-dimensional finite element analysis. And the procedure can be also generalized to bi-dimensional frames. So I've concluded. Thank you for your attention.
Is there any question? Please.
Perhaps I didn't hear right. In your finite element model, you model the beam as homogeneous orthotropic material, or you model independently?
No, it's an homogeneous material whose properties are dependent on the single components.